Flipped classroom video for further maths unit 2, correlation. The correlation between two random variables is the measure of the extent to which a change in one tends to correspond to a change in the other one. If the change in one corresponds to a change in the other in the same direction, there's a positive correlation. If the change between them are in opposite directions, there is a negative correlation. There's an example of a positive correlation. As one increases, so does the other one. A negative correlation, as one increases, the other decreases. So we're getting a negative gradient. And then an example of no correlation here. We can work out from the pairs of data the sum of each x, square each x and add them up, the sum of each y, the sum of each y squared, and then the sum of each x multiplied by y and then added together. And then we can calculate summary measures for these observed sets of bivariate data, two sets of data varying. So we've got an SXX, which is defined to be the sum of each x with the mean of x taken away from it and then squared, but that can also be worked out as the sum of x squared minus the sum of x all squared over n. Similarly, S of yy would be the same with y, so each y with the mean of y taken away from it and squared, which can also be worked out as the sum of y squared minus the sum of y all squared over n. And then x times y, each x times y can be worked out to be the sum of each xy minus the sum of x times the sum of y all over n. And we use that in quite a few of our calculations. These are given in the information book. Now, one measure of the correlation between random variables is the correlation coefficient rho approximated by r. And this is given as, that's the same as the SXY on the top divided by the square root of the SXX times the SYY. So that's the approximation from the data we've observed to give us a measure of the correlation. This is called a Pearson's product moment correlation coefficient, and this is also given in the information book. Interpretation of the product moment correlation coefficient. A plus means a perfect linear correlation, so it would be following a straight line with a gradient of 1. A minus 1 means a perfect negative correlation, so it would follow a straight line with a gradient of minus 1. And a 0 would mean no correlation between the two variables. So we can work out a measure of the correlation from our observations. Example: the length y of a rod was measured at varying temperatures x degrees Celsius, the results obtained being as shown in the following table. Assuming that the temperature levels are accurate and that the measured lengths are subject to error, find the value of the Pearson's product moment correlation coefficient and interpret your results. So first off, we have to work out the sums, the relevant sums we need. So the sum of x, add up all the x and we get 300. Add up all the y and we get 51.8. Add the x multiplied by y, so 20 times by 10 plus 40 times by 10.2 and so on, and we get 3,144. Add up all the x squares, so 20 squared plus 40 squared plus 60 squared and so on, and add up all the y squares. So we've got all those as the sums that we are going to need. So the first summary measure we're going to work out is the SXX, which is the sum of all the x squareds minus the sum of all the x all squared divided by n. So we can put in our sum of x squares, which is 22,000, minus the sum of all the x, which is 300, square that, and divide by n, which is, there are 5 measures, pairs of measures. Work that out and we get 4,000. The SXY first then. So sum of xy is 3144 minus the sum of x times the sum of y over n. So 3144 minus 300 times my 51.8 over the n, and we get 36. The SYY gives us the y squared, sum of y squared, which is 536.98, minus the sum of all the y, all squared, 51.8 all squared, divide by 5, and we get 0.332. So working out the Pearson's product moment correlation coefficient, we need to use this formula. So we get 36 for the SXY divided by the square root of 4,000 multiplied by 0.332, which gives us 0.987. Now remember, plus 1 was a perfect linear correlation, so we have a very high positive linear correlation. As 1 increases, as the temperature increases, then so does the length. Another example, in a training scheme for young people, the average time taken for each age group to reach a certain level of proficiency was measured. The data are shown in the table. So age against the average time taken for a task. So find SXX, SYY, SXY. Use your answers to calculate the product moment correlation coefficient R and describe and interpret the relationship between average time and age. So there's various sums, the sum of x, the age, the sum of each x squared, so 16 squared plus 17 squared, and so on. The sum of each y, the sum of each of the y that's been squared, and then the sum of the product of x times y. So we have these values to help us. So the SXX was sigma x squared minus sigma x all squared over n. So we have 4285 minus 205 all squared over 10. There are 10 values, and we have 82.5. The SYY, so we have the sum of y squared being 861 minus the sum of y all squared, which is 91 all squared, divide by 10. And we get 32.9 as SYY. The SXY is the sum of the product of each pair minus the sum of the two separately over n. So we get 1821 minus 205 multiplied by 91 divide by 10, and we get minus 44.5. Therefore, our product moment correlation coefficient gives us minus 44.5 divided by the square root of 82.5 multiplied by 32.9, and we get minus 0.854 as the correlation coefficient. It's a negative correlation, so we have a fairly strong minus 8.5 correlation. As the age increases, the time taken decreases. Sometimes it is not possible or not worthwhile to measure certain variables. For example, suppose a manufacturer of tea produces a different number of brands You could taste each blend and place them in order of preference. Similarly, it may be quicker to arrange a group of individuals in order of height, rather than measure each one. In this case, we use the Spearman's rank correlation coefficient instead of the product moment correlation coefficient. So we are ranking them. This is a special case of the product moment correlation coefficient where the data is ranked first before calculating the coefficient in the same way. But an easier way would be to take the difference in ranking and use the formula. So the R with S suffix, that's the Spearman's rank correlation coefficient, would be 1 minus 6 times the sum of the difference squared. D is the difference between the rankings, so square that, so we get rid of the minuses, and we divide by n times n squared minus 1. It makes no difference if you rank the smallest or largest as 1, the next as 2, etc., provided you do the same to both the x and the y. This time, plus 1 means that the rankings are in perfect agreement. Minus 1 means the rankings are in exact reverse order, and 0 means there's no correlation between the rankings. Remember, we're talking about ranked data now. So another example, during a cattle show, 2 judges ranked 10 cattle for quality according to the following table. So find Spearman's rank correlation coefficient between the 2 judges and comment on the result. So Judge A's rankings we have along there. Judge B's rankings we have along there. The difference between them, so if it's A take away B, we have minus 2. 5 take away 6, minus 1. 2 take away 2 is 0. 6 take away 7, minus 1. Minus 1, 0, 2, 3, 1, 1. Now because we have minuses here, we need to square these. So we have 4 for the square of the first. 1, 0, 1, 1, 0, 4, 9, 1 and 1 for all the differences between the rankings squared. Add those and we get 22 for the sum of the d squared. Therefore, using the Spearman's rank correlation coefficient, so R with the suffix x, we have 1 minus 6 times the sum of the d squareds over n squared minus 1. So we have 1 minus 6 times 22. There's 10 in n multiplied by 10 squared minus 1 is 99. And that gives us 0.867 to 3 decimal places. So there's a reasonable degree of agreement between the 2 judges. We're talking about decisions of 2 judges. So that's an example of the Spearman's ranked correlation coefficient. Another one, the number of goals scored by football teams and their positions in the league were recorded as follows for the top 12 teams. So we have the teams, the goals scored and the league positions. Calculate Spearman's rank correlation coefficient for these data. What conclusions can be drawn from the result? So I've put the league on top and then the goals underneath. So we'll rank the goal. As the league is ranked already, we'll rank the goals. So there's the first one, there's the second one, there's the third one, the fourth is this one, the fifth is this one, and so on. So I've ranked the goals. Take the league and the goals away from each other, and I've ignored minuses because I'm squaring anyway. So take them away from each other. So we have 0, we have 2, we have 1, we have 1, we have 2, 4, 1, 2, 4 and 1. Squaring those, we're getting those values, add those up and we get 48 for the sum of the differences squared. Spearman's rank correlation coefficient, so 1 minus 6 times 48 divided by, there's 12 in the league table, so 12 times 12 squared minus 1, 143, and that works out to be 0.832. The league position and the number of goals scored show a fairly strong positive correlation. Now, we need to test the hypothesis that a correlation coefficient is 0 or not, because sometimes the decimal can be quite far away from 1 or minus 1 and maybe 0.5 or something, and we need to see, have we got we can test to see if a correlation exists or not. So we are going to say that it's 0. We're going to test that it's 0 against it's not. How near must our value be to 0 to say that there is no correlation? We are estimating the true correlation rho between x and y experimentally with observed values of little x, little y. Suppose that the observed data can be modeled by variables x and y, which are jointly normally distributed, and the product moment correlation coefficient R is an unbiased estimate of the true correlation. Then that's our graph for R. So we are normally distributed. We are interested in a value of C which R exceeds with a small probability. That's called a critical value. And if it's above that, then we are going to reject H0. So on page 13 of your tables book, table 9, you have critical values for some significant levels of R, the product moment correlation coefficient. So rho is the true correlation. We approximate this with little r. We need to set up the hypothesis, being as we're testing each time we do it. So we are saying our rho is 0, with either rho being not 0, so which would be two-tailed, so both sides, or rho is 0 against rho is greater than 0, being positively correlated, or rho is 0 against rho is less than 0, and both those would be a one-tailed test. For testing hypotheses using Spearman's rank correlation coefficient, we use table 10 on page 14 of the tables book, setting up the same manner hypotheses first. Example 5. Using the values, so all the sums have been worked out, calculate the product moment correlation coefficient between these 20 pairs of readings, and using a 0.05 significant levels, 5%, test the hypothesis that rho is equal to 0 using a two-tailed test. So we are testing rho is equal to 0 against rho is not equal to 0. So we need to work out our summary measures first. So Sxy would be the sum of the product minus the sum of each xy separately multiplied and divided by 20. So we get 30 for Sxy. Sxx similarly, so 35 minus 20 squared over 20 gives us 15. Syy is 130 minus 35 squared over 20, giving us 68.75. Our product moment correlation coefficient is 30 divided by the square root of 15 multiplied by 68.75, giving us 0.9342. That's a very high value anyway, but we'll use it to test. So from table 9, we've got n is 20, is two-tailed at 5%. So we're looking at 5% two tails down to n is 20. So that is the value of our critical value of R, plus or minus being as it's two-tailed. So our critical region is below minus 0.4438 or above plus 0.4438. Our observed values is well within this region, so we reject H0, accept H1. There is evidence to suggest that the correlation is not zero, even though we could see from the value. Anyway, another example, the following table shows the marks attained by 8 students in English and Maths tests. Calculate the product moment correlation coefficient. The teacher thinks that the correlation between the marks is likely to be 0. Test the teacher's idea at the 5% significance level. So we're testing that the hypothesis that rho is 0 against that rho is not 0. So two-tailed test, 5% level. So first of all, we need to calculate all our sums. So the sum of x, i.e. the English marks, the sum of the x squareds, the sum of the y, i.e. the mathematics marks, the sum of the y squareds, and the sum of the product of each one. So then we get our summary statistics. So SXX is the sum of the x squareds minus the sum of the x all squared over 8, because we've got 8 of them. Work that out, and we've got 220 for SXX. SYY would be sum of y squared minus the sum of y all squared over 8, which comes out to be 309.875. Then the SXY is the sum of the product minus the product of the sums over n, and that gives us 179. So we work out our correlation coefficient, and we get 179 over the square root of 220 times 309.875, and we get 0.68556. So now we are going to test this so we'll be looking at table 9 with n equal to 8, 5% two-sided. So table 9, 5% two-sided, it's two-sided, so our R from the table, so our critical value of R is 0.7067. So our critical region is less than minus 0.7067 or R greater than 0.7067. Our observed value is not within this critical region, therefore we have to keep H0. There is a zero correlation, there is no correlation at the 5% level. Another example, each of the teams in the school hockey league had the total number of scores goaled by them and against them recorded with the following results. Investigate whether there is any association between the goals for and those against by using Spearman rank correlation coefficient. Use a suitable test at the 1% level to investigate the statement. A team that scores a lot of goals concedes very few goals. So we're looking for a negative correlation there. So we are looking at testing is rho equal to 0 against is rho less than 0. So ranking the goals for, so our highest score is 42 for G, our next best is 40 for B, and so on, ranking the goals for. Ranking the goals against, our highest against was D at 42, then F at 38, and so on. So we've ranked them all. We need to find the difference. disregarding the plus and minus because we're going to square them. So the difference between the two sets of rankings we've got there, square those, and we have 16, 1, 1, 25, 4, 4, 25. Sum those and we get the sum of the difference squared is 76. So our Spearman's rank correlation coefficient is given by that. Work that out and we have minus 0.357, which looks very low indeed. So table 10 we need to look at. Table 10 says critical values of the Spearman's rank correlation coefficient. One-tailed at 1% and a n is 7 gives r, and we're looking at the negative values with, so minus 0.8571 is our critical value. So we're looking at the critical region being below that. Our observed value is not in the critical region, so we reject H1. There is sufficient evidence to say there's no correlation between the goals for and the goals against. And one last one. For one of the activities at a gymnastic competition, 8 gymnasts were awarded marks out of 10 for each of artistic performance and technical ability. The results were as followed. The value of the product moment correlation coefficient for these data is 0.774. Stating your hypothesis clearly and using a 1% level of significance, test for the evidence of a positive association between technical ability and artistic performance. Interpret this value. So we're looking at table 9. First of all, we want to set up our hypothesis. So we're looking for H0, that row is 0, against, we want a positive association, that row is greater than 0. Table 9, n is 8, there's 8 gymnasts. 1% one-sided gives the critical value of r is 0.7887. Our value, so our critical region is greater than that. So our value is not within this critical region, is below that. So we say that there is insufficient evidence of a positive association between technical ability and artistic performance at the 1% level. Part B, calculate the value of the rank correlation coefficient for these data. And stating your hypothesis clearly and using a 1% level of significance, interpret this coefficient and then explain why the rank correlation coefficient might be better one to use with these data. So we are now going to rank them. So technical ability, so our top technical ability was C at 9.5, then G at 9.4 and so on. So ranked technical ability. Ranked artistic performance, we have our top one as 9.1 for H. Our second one was C at 8.2 and so on. Working out the difference, disregarding the minus and squaring. Our sum of the squares of the difference is 10. So working out the rank, Spearman's rank correlation coefficient. So it's 1 minus 6 times the sum of the d squares, 10, divided by n, which is 8, and multiplied on the bottom by n squared minus 1, which is 64 minus 1, which is 63, and we get 0.881. Our hypothesis was rho was equal to naught against rho greater than naught, and we are looking at table 10 now because it's Spearman's rank correlation coefficient. N is 8 and it's one-sided 1%, so our critical R was 0.8095. So our critical region is greater than that. Our observed critical value was 0.881, which is within the region, is greater than the critical value. So we're keeping H1. There is evidence of a positive correlation between technical ability and artistic performance. Now, why is the rank correlation coefficient better than the product moment correlation coefficient? Well, two suggestions are they're judgments, not measurements. The judges are given these scores, so they're not measurements of anything, and it's unlikely that the scores will be normally distributed. So there's two reasons why the ranking would be a better one to use. And that's the end of the flipped classroom video on correlation.